All right, hello everyone. Welcome back to our weekly live stream for Physics 8B. This week we're going to be talking about induction, and induction is a tricky one. It's interesting because there's very little material, but it is still very confusing. So conceptually, it's hard to wrap your head around induction, but conceptually there isn't much. There really is just Lenz's law and Faraday's law, and the rest is a lot of practice to make sure that when you deal with an induction problem, you follow the steps in a certain fashion so that what you worry about is not the magnetic flux, but how the magnetic flux changes with time, because that is what matters. And the biggest conceptual mistake is to focus on flux and not on how flux changes. And once you start doing that, things kind of fall in place. Lenz's law is very easy to apply to find I induced in direction, but to find I induced in magnitude, we'll actually have to first apply Faraday's law and then use either the loop law or Ohm's law. And so the goal today is going to be to go over two classic types of problems in induction. One where the magnetic flux changes because the magnetic field changes, and the other where the magnetic flux changes because the area through which I have magnetic flux changes. That'll be the rod on rails problem, which is an extremely classic problem. There's so many exam problems that are based on this rod on rails problem that it's really important that we talk about it and that we understand how it works. So I'm going to try to spend as little time as I have to on the concepts, because again, there's not that many concepts. It is far more important to understand how you take those concepts and you apply them in problems. And that's really what I would encourage you to focus on when it comes to induction. Like, make sure you do enough problems that you recognize which situation you're in. Like, why does the flux change? Can I write the flux down, and then can I evaluate its change with Faraday's law? And then from there, okay, you can get I induced and all of that, but that's the hardest part. So just as a quick reminder, if you want to follow these live streams in, one, how do you say, the same in one area where it's all put together and everything's there and you don't have to browse YouTube, you can go to slackademia.com and enroll into the free Physics 8B live stream course, and you'll find everything in there, all the live streams, along with the solved homework problems. So having said that, let's start talking about induction with simply a definition. Definitions are pretty nice. We should agree what we're talking about. And the definition of induction is the production of a voltage, which we call EMF or induced EMF, and we denote it by epsilon induced, across a conductor because of its interaction with a varying magnetic flux. And the key is that it's not just magnetic flux, it is a varying magnetic flux. So in order for there to be induction, there has to be a change, specifically a change in the magnetic flux. But the short of it is that if you move a wire through a magnetic field, then you will find that you create a current in that wire, which is induction, and it comes from the voltage, the EMF that has been produced across the wire. You would also find that if you held the wire still and you had the magnetic field change in magnitude, then you would also create a current in the wire, which is unexpected. And so the idea is that it's something that took a long time to discover because it is based on change. And well, if the change happens quickly, then by the time you go back and you try to look at your instruments that might be very primitive instruments at first, whatever happened you missed, right? Maybe the instruments are over there and you do something here and you go check it out and there's no measurement to be seen because as fast as it appeared, the phenomenon is now gone. So induction is something that took a while to be stumbled upon, and it's not very intuitive why either moving a conductor through a magnetic field or having a conductor sit in a magnetic field that changes with time would cause a current, but yet it does. And so we're going to try to focus on those two cases in the problems that we do today so that we see how to quantitatively account for that and find the direction of the induced current, but also the direction of, or the magnitude rather, of the induced current. Okay, so that's the definition. So we have to have a varying magnetic flux that interacts with a conductor. That induces a voltage across the conductor, and of course, because it's a conductor, charge is free to move, so that drives a current through the conductor, which will be called an induced current. Now we have two laws when it comes to induction. We have Lenz's law, and Lenz's law is useful to find the direction of the induced current. In fact, that's all we use it for, and we specifically use Lenz's law to find the direction of the induced current. There's other ways. You could use Faraday's law, but we're going to use Lenz's law for direction, Faraday's law for magnitude. Okay, so Lenz's law states that there's no easy way to put it, so let's try to put it in the simplest terms possible. I induced flows in such a way that it creates B induced, an induced magnetic field, to oppose the change in magnetic flux. And it's just one of those things that is a lot harder to word in the most general case possible, or the most general way possible, as opposed to when you go to apply it in a problem, it's actually pretty easy to apply. So it's a lot easier to apply it in practice than to phrase it so that it's general enough that it always works. But the idea is that epsilon induced will drive I induced in a direction such that I induced creates an induced magnetic field that opposes the change in magnetic flux. So we'll unpack that when we do problems, but that is Lenz's law. Lenz's law is what we use to find the direction of I induced. Okay. Now then we have Faraday's law. Now Faraday's law we're going to use to find the induced EMF, so epsilon induced, and then from there, Ohm's law or the loop law will get us I induced in magnitude. But Faraday's law, all it does is it gives us epsilon induced. Okay, and so I'm going to draw something that is going to be as general as possible. It's not going to be very helpful necessarily, but I'm going to have a loop, right? This is a conducting loop. And I don't want it to be any special shape, but in practice it might be a rectangle or a circle or something typically for which the area is easy to compute. So maybe even a triangle. Not something like this. It's very hard to find the area of this thing. Right? But the conducting loop has a certain area. And let's say that there's a magnetic field everywhere here, I don't know, coming out of the page, let's just say. Right. Some device, a magnet or a machine or something, is creating a magnetic field that comes out of the page. And let's assume that it's a uniform magnetic field. It's the same everywhere in magnitude and direction. Right. Then the magnetic flux through the conducting loop is going to be phi b. So we'll start, before we define even Faraday's law, we'll define the magnetic flux. Okay, now the magnetic flux is going to be the same thing as the electric flux, it turns out. Right? Electric flux counted the number of field lines that went through a surface, of course, of electric field lines. Well, magnetic flux is going to count the number of magnetic field lines that go through a surface. Right? So I expect the math to be the same, right? This is going to be the integral over some area of B dot dA, just like I had the integral of E dot dA in Gauss's law. And then this, if I'm lucky, is going to simplify because it's going to be the integral of B cosine theta dA And if B is uniform, which is very often the case, then I get B area cosine theta. So this is if B uniform. Okay, well, and if B is not uniform, well, different story altogether. Okay, we have to carry out the integral. That's not a very nice problem. There's some old exams where that's been the case, and so you can see how that works in there. But again, my goal today is not to, make it too complicated right off the bat. We want to break down induction into simple terms so that we know how to do the bulk of the classic problems where B is in fact uniform. Now we can always worry about B not being uniform later, but let's at least agree that what we try to do is find the magnetic flux, which is going to be B times area times cosine theta, and then we're going to plug that into Faraday's law. Now, one thing that we might want to say is, what is dA? We kind of already know what dA is from Gauss's law, but just as a reminder, this is my conducting loop, yeah? So I'm going to look at it from the side like this, and perhaps, now this is a view in perspective, right? It's the same, it's meant to be the same loop. Okay, and if I look at it from the side, I'm going to see B coming out like this, right? Hopefully that makes sense. Okay, that's B coming through my conducting loop, or through the area bounded by the conducting loop. And now dA is going to be the vector that's perpendicular to my loop. Now, there's two options for dA, yeah? It could be like this. That would be an option. That's perpendicular to my loop. But it could be like this. It could be pointing down. Both are perpendicular. Both are valid choices. But if I can actually choose, then I would prefer to keep dA in the direction of B, because then I get cosine of 0 here instead of cosine of 180, because if I use this as my dA, the one that points down, then B points up, dA points down, the angle between the two is 180. So I don't like cosine of 180. I would prefer to avoid all that if I could. So if it were up to me and I could choose either of the two, I would do this. I would put dA perpendicular to the loop in the direction of B. Now the thing is, it's not always the case that B is perpendicular to the loop. It's very, very, very common, but it doesn't have to be the case. However, dA does have to be perpendicular to the loop. You don't get to negotiate that, okay? And so that's what dA is, and we have a little bit more wiggle room here because when we used dA in Gauss's law dealt with closed surfaces like spheres or cylinders. If you have a closed surface, you have to choose the outward normal. That's the default, okay? That's why outward flux is positive, and it's a convention from math. But here, the loop that I drew is just a flat, it's a slice of something, right? It's like a chip or whatever. It's not a closed surface, right? So I can choose whatever I want. As long as dA is perpendicular to it, it can point up or it can point down. There's no requirement on dA. So anyway, that is what dA is, and as you will see, overwhelmingly the problems that we deal with have a magnetic field that is perfectly perpendicular to the surface through which there is magnetic flux. Okay, but magnetic flux is the equivalent of electric flux just when it comes to magnetic fields. It counts how many field lines go through a surface. Now the main difference also with electric fields is that we did not care how the electric flux changed. We just set it equal to Q enclosed over epsilon naught with Gauss's law. But when it comes to Faraday's law, what we care about is not the magnetic flux, but how the magnetic flux changes. And so Faraday's law is going to tell us that epsilon induced, the induced EMF around the loop, is going to be equal to minus d phi b dt. So mathematically, we're saying, yeah, it's not really just the flux that matters, it's how the flux changes, right? And epsilon induced is going to drive I induced. So let's just, for the sake of argument here, assume, just to illustrate this, B decreases in magnitude. Let's just assume that's the case. Now, it's the same everywhere, right? So B is uniform, meaning wherever you look, you see the same B. Now, it might decrease, but still, it's the same everywhere, right? Like you look at any point, at a given moment in time, it's the same value of B. Now, over time, it could decrease or increase. That doesn't prevent it from being uniform. Okay, so then if B decreases in magnitude, and I look at this thing here, my flux out of the page decreases, okay? Because B becomes weaker. If B becomes weaker, flux decreases. All right, now if B decreases and my flux out of the page drops, I need B induced to come out of the page to oppose the drop in magnetic flux out of the page. It's trying to sustain the magnetic flux out of the page as B, the original B, drops. The only way I get B induced pointing out of the page is if the induced current, which is what creates B induced, flows counterclockwise around this loop, right? Thumb out of the page, my fingers wrap around counterclockwise. I induced would flow counterclockwise around the loop. But it's very important to realize that it is not B induced that creates I induced, right? We just did magnetism. We learned in magnetism that it is currents that create magnetic fields, not magnetic fields that create currents, okay? So I induced creates B induced. It's just that when it comes to reasoning out the direction of I induced, it is usually a lot easier to work in reverse, where we say, okay, flux out of the page drops. I need B induced out of the page, therefore. Okay, if B induced is out of the page, then I induced is counterclockwise. Reasoning backwards is very easy, or it makes it very easy to find the direction of I induced. It does not mean, however, that B induced created I induced. That's not the case. I induced creates B induced, okay? And so Faraday's law effectively tells me epsilon induced, which is the induced EMF that is going to drive I induced around the loop. Okay, so in a sense, my conducting loop, because of this changing flux, starts to behave like a battery. All of a sudden, it starts to drive current through it, even though there is no battery. It's just a wire. Okay, so that's what's surprising about induction, is that these conductors, or these conducting loops, start to behave like little batteries because there's a magnetic flux that changes as time goes on. So the goal then is going to be the following. We are going to look at two very classic types of problems where the flux changes either because the magnetic field changes, just like we did here, or because the magnetic field doesn't change, but the area of my conducting loop, or the area bounded by the conducting loop, changes. It could decrease or increase, we don't know, but that's two ways in which we can change flux. Okay, and so those are two archetypal problems, and we're going to solve one of each. Okay, so let's come down here. Let's have a look at this thing. And it's also meant to kind of, slowly work us up to knowing how to deal with these induction problems. So we're not going to do a problem that's insanely difficult right off the bat. So here we have a square loop, side length D. It contains a light bulb with resistance R, and it is perpendicular to a uniform magnetic field pointing into the page. Okay, so B points into the page everywhere, and at any given moment in time, B has a certain magnitude that is the same everywhere. But now we're told if the magnitude of the magnetic field linearly increases from 0 to B max over the time capital T, describe qualitatively the general phenomenon occurring in the loop for T between 0 and big T in terms of voltage, current, and magnetic field. Okay. So, we are told that B increases linearly from 0 to B max over a time capital T. Okay, maybe let's just graph that. Okay, so this is time, and this is B. B starts at 0, and in a time capital T reaches a magnitude B max. Okay, so it linearly increases. It looks like this. That's the only option, yeah? Okay. So B is indeed a function of time. Even better than that, it is a function of time that I can work out because it's pretty easy to find the equation of a line that goes through the origin. Right? All I have to do is find the slope, and that will relate B to the variable t. Okay, so if I wanted to find B as a function of t, I would find the slope here. All right, now the slope m is equal to, well, delta y over delta x, or rise over run. Okay, rise is B max over run is capital T, and so this is B max divided by capital T. Okay, that is the slope times the variable t plus the y-intercept, where the y-intercept is 0. It goes through the origin. At t equals 0, b is 0. So, okay, I have a function of time, b, and it tells me that b increases with time. If b increases with time into the page, because b is into the page, then the flux through the area bounded by my conducting loop increases into the page. If flux increases into the page, B induced must oppose the change in flux, and therefore B induced must point out of the page to oppose the increase in magnetic flux into the page. The only way I get a B induced pointing out of the page is if there's an induced current in this loop that is going around the loop counterclockwise by the right-hand rule. Wrap my fingers in the direction of I induced, my thumb points along B induced. So what will happen is that just by varying the magnetic field in strength through this loop, I'm going to get a current induced in the loop that will cause the light bulb to turn on. Okay, and so again, not very intuitive, not really expected, but if B changes, I get a current through the loop, and that current, if it goes through a light bulb, is going to turn on the light bulb. Okay, so let's find the voltage, the current, and, well, the magnetic field. We can only find the direction, but that's fine, we can do that too. So B induced points out of the page, we kind of already know that. But let's find the flux so that we can get the induced EMF, epsilon induced, and the induced current. Okay. Now, we'll start by writing down what we just said, which is that for t going from 0 to capital T, B increases into the page causing the magnetic flux Phi to increase into the page. And then by Lenz's law, B induced must point out of the page with I induced flowing counterclockwise. All right. Now let's quantify this flux, right? So before I even apply Faraday's law, I want to figure out the flux. And I always want to ask myself, why is the flux changing? Right, here it's changing because B is changing. the area of the loop, or the area bounded by the conducting loop, doesn't change. It's fixed. So the only reason flux changes is because B increases. Okay, so my flux is going to be, and it's just going to be B, which is a function of T, times the area, and then this is a bit overkill, but I'll write it anyway, cosine of 0, where I can choose dA either into the page or out of the page, because dA needs to be perpendicular to the loop. Okay, but if I get to choose, I'm going to put dA in the direction of B so that I get cosine of 0, which is 1. And then I can say, okay, well, I know what B is as a function of T. This is B max capital T times little t multiplied by the area. Well, it's a square with side length d, so that's just d squared. So this ends up being B max d squared over capital T times little t, time, the variable for time. Okay, so that's my flux. By Faraday's law, epsilon induced is minus d phi b dt. Okay, now that's pretty straightforward. I'm going to get this as a constant times t, so okay, if I take the derivative of 7t, I get 7. In other words, if I take the derivative of flux here, I am simply going to get B max d squared divided by capital T. Okay. Now, something worth noting is the following. The minus sign here is actually irrelevant. The reason it's irrelevant is that we use Lenz's law to find the direction of I induced. In other words, I already know that I induced has to go counterclockwise. The minus sign would tell me that if I were very careful in setting up Faraday's law and I use the right-hand rule as my sign convention, you know, that if B is into the page, then counterclockwise is negative because into the page is associated with clockwise, then the minus would tell me the direction of I induced. So in practical terms, the minus here is irrelevant in 8b. However, even though it's irrelevant, I would strongly suggest that you do not forget to write it on your exam, okay? Because Faraday's law is not epsilon induced is equal to d phi b dt. It is minus d phi b dt that you have to write. So always write the negative sign. Just know in the back of your head that, or the back of your brain, that it's irrelevant. It doesn't mean anything. All we're going to use epsilon induced for is to find the magnitude of I induced, which we'll just take absolute value of epsilon induced and divide by the resistance of the loop in this case. Okay. So to find I induced, we're just going to write Ohm's law, and we're going to say that I induced, which we already know flows counterclockwise, is absolute value of epsilon induced divided by R, the resistance of the light bulb, and that's going to be B max d squared over RT. Okay, so that is how I would find I induced. I would first need to apply Faraday's law. Okay, keep in mind that Faraday's law is the only new equation that we have for induction, and it does not give me I induced directly. First it gives me epsilon induced, and then from there I can find I induced. Okay, and so that was really, this is really question 2. I mean, should have put that there. Question 2 is asking me to find the induced voltage, which I just did. First we evaluated the flux, then Faraday's law, that's epsilon induced, and then we can figure out from Ohm's law, yes, the induced current flowing through the loop. Now we also want to sketch the induced current as a function of time.
in this particular case, it is very straightforward. We're going to have time go from 0 to t. And if I want to graph I induced is just a constant current. Right now, is it always the case that I induced is constant? No. Sometimes I induced will decrease with time or increase with time. It depends how complicated the expression of the flux is. Sometimes flux is more complicated than just a constant times time. That makes epsilon induced more complicated, and in turn I induced more complicated. But in this specific case, again, let's do the simple cases first. I induced is constant. Now, there is something to be said, which is that if in fact after time capital T, we stop increasing the magnitude of the magnetic field, then flux is no longer going to change, right? So if we ramp up the magnetic field to B max, but then after capital T we held it steady at B max, then flux would be flux. It would never change. It would be just B max times the area, done deal. No change in flux, no induced current, because induction is a change-based phenomenon. So if I make that assumption, then I would probably amend my graph to look like this. I would say, okay, after time capital T, I induced falls to 0, assuming I maintain B at B max. Okay. Now, question 3, what happens if the magnetic field is reduced at the same rate as it was previously increased? Okay. So now we're saying that this was B as a function of time. Right? What if this happens? Right? What if we have B is going to grow from 0 to B max in time capital T? That is going to give me a certain slope. What if we drop it back to 0, basically in the same amount of time, right? Magnetic field reduced at the same rate it was previously increased. So now the magnetic field is going to drop back to 0 with a slope here that is going to be m is equal to minus B max over t. Right, it's rise over run. It's not a rise, it's a drop divided by the run t. So we get minus B max over t. Okay, now what happens if that is the case? Okay, well, let's very quickly draw our circuit over here, okay, to match that. Now, B is not going to change direction, just so we're clear. We're just saying that the magnitude of B after it peaks drops back to 0. But that does not mean that B stops pointing into the page. In fact, B at all times points into the page. Okay. But now what's going to happen is that I'm going to find that the magnetic flux into the page decreases with time because the magnitude of B drops. So if flux decreases into the page, I need B induced to oppose the change in flux, and here it's going to try to maintain flux into the page, meaning that the only way that I get B induced to point into the page is if I induced flows clockwise this time around the circuit. So what happens if the magnetic field is reduced at the same rate as it was previously increased is that I induced changes direction, because now B induced has to maintain flux into the page. But if we're actually going to drop B at the same rate linearly, then I induced in magnitude will not change, right? Because what we'll get here is a flux that's going to be this. It just will be negative. That'll change this into a positive, but we just said the sign of epsilon induced doesn't matter, just its magnitude. And I induced will end up being the same. So here we will still have I induced will be in magnitude, B max d squared over RT. So I induced would flow in the opposite direction, but with the same magnitude. Okay, because in magnitude, the rate at which we change the magnetic field is the same. Again, induction is a change-based phenomenon, but if the rate at which the change occurs is the same in magnitude, then there's no reason why I induced should be different in magnitude. Okay, and so then question 4 asks, well, based on your observations of the brightness of the light bulb, how could you tell if the rate of change of the magnetic field is modified one way or the other, right? Increase at a different rate or decrease at a different rate. How would you be able to tell? Okay, well, look, the brightness of the bulb is proportional to I induced squared, which is B max squared. I'm going to write it like this, over T squared multiplied by D, well, actually D to the 4, really. D to the 4 R squared. Okay. Now, if you're wondering where that comes from, that's because the power dissipated by a resistor is Ri squared. And effectively, in this class anyway, light bulbs are resistors that produce light. Okay, so the brightness of a light bulb is given by Ri squared. It's proportional to I induced squared. And if we look at this expression here, which is just this being squared, then we're going to find that really what we have is the following, right? It's B max over T, the whole thing squared. Okay, but this here is the rate at which B changes. Okay, so what happens is that if I change that rate, it's going to translate to I induced. Now, I don't have to change B linearly. I could, right? I could make B, instead of reach B max in time t, maybe it reaches 2B max. So it's still linear, but it goes twice as far in terms of magnitude of the magnetic field. But I could also have B very quadratically with time, or be any function of time. The point is, the rate of change of B is going to show up in I induced. And in particular, if it's just a linear rate of change, then it's going to show up here as the slope that's going to be squared. And so the greater the slope in magnitude, the greater I induced, and therefore the brighter the bulb. Okay? So the answer to question 4 is that, well, the rate of change of B directly affects the brightness. The greater the rate of change of the magnetic field in magnitude, the brighter the bulb, and the smaller the rate of change of the magnetic field in magnitude, the dimmer the bulb, which makes sense. Again, induction is a change-based phenomenon. If the rate of change of B is very small, well, that's not a lot of change, and so yes, the light bulb will, shine, but not very bright. Whereas if there's a very abrupt change, all of a sudden the light bulb will light up very quickly and very bright, because the big change means that there's a bigger response in terms of I induced, right? A stronger induced current because of it. Okay. So, this is for a problem where induction occurs because magnetic flux changes, and magnetic flux changes because the magnetic field changes in magnitude. Either you find the function B of t, which we had to do. We were given enough information to graph it and then to find the function. Or sometimes the function might be given directly to you. Okay, but in any case, it is a problem where induction occurs because the magnetic field changes with time. And you find B of t, or maybe you're directly given B of t, and then you're off to the races. You can do Faraday's law and the Ohm's law and whatever. However, it's not the only way that magnetic flux can change. And so magnetic flux might also change because the area changes, but B is the same. Okay, so here we have two parallel rails that are connected here with a wire and a light bulb that has a resistance R. And the magnetic field everywhere points into the page and is uniform, so it's the same everywhere, but it's also constant. It does not change as time goes by. However, because this conducting rod is moved to the right across as it rests across the rails, well, the area here of my conducting loop through which there's magnetic flux is going to, well, increase because the rod moves to the right. That will cause the flux to change. So now we have a problem where the magnetic flux changes, but because the area of the conducting loop changes. Now, just a side note, because as I say this out loud, I'm remembering getting this question a few times, which is a classic question. It's like, well, how do I know where my loop is? Usually there's only one loop, right? So like, I mean, this case is pretty obvious. That's the loop. There's only that. But then this one, maybe it's not so obvious because you're like, well, I can see how this is a loop, but that would mean that only the left-hand side counts. Is it not the case that this also counts? It's like, well, that's not a loop, right? I would need the two rails to be connected here so that I would have a loop there. In fact, then I would have two loops, right? And I have to worry about the flux through each one. Flux through here would increase, flux through here would decrease as the rod moves. Now that is actually a classic exam question that is a variation of this problem where we connect the two like this and then we're like, oop, okay, what happens? You know, maybe you put another light bulb here or whatever. But that's a different story. So here the point is there's only one loop. It's on the left-hand side. This is the loop, and therefore that is the area that I'm interested in when it comes to finding the magnetic flux. Okay, so let's talk through what happens, and from a conceptual level first, so that we agree on what happens, and then we'll go through the questions of finding the induced EMF and the power dissipated by the light bulb and so on and so forth, because this is such a classic problem that it's not even funny. I mean, there's so many variations of the rod on rails problem that, you know, you being able to solve them depends upon you understanding this problem and how we set it up and how we solved it. And then we can make variations, right? We can be like, oh, well, okay, we'll connect this and we'll put another bulb here. Or, oh, wait a minute, I want to add a resistor here, what happens? Or maybe I want to slant the bar at a certain, 30 degrees from the vertical or whatever. Those are all classic variations. Sometimes the rails are not parallel. They all work the same way. They're all based on the same approach and the same method for solving. So let's take this thing here. Let's make a copy. And let's talk through what happens. Okay. So we are told that the two rails are connected to a light bulb in such a way that any induced current will cause the light bulb to glow, just like the previous problem. Should any current flow through this loop, it will flow through the light bulb. The light bulb will light up. Okay. And so conceptually, before we even start finding epsilon induced, what we have here is an area that is going to increase with time as the rod moves to the right. If the area increases with time, then flux into the page increases. And flux is into the page because B is into the page. So as the rod moves to the right, flux into the page increases.
by Lenz's law, B induced must oppose the change in flux.
So if flux increases into the page, I need B induced to come out of the page. Okay, because B induced is going to oppose the increase in flux. Now what that tells me is that not only do I have a current, because I induced doesn't create B induced, but that current is going to flow counterclockwise by the right-hand rule. All right, and therefore, yes, the light bulb will light up because there is a current flowing through it. Okay? So that is what's going on. So maybe we write that out real quick and say, as the rod moves right, phi B increases into the page, because the area of the loop increases. And then by Lenz's law, B induced must point out of the page with I induced counterclockwise.
Okay, so that is what's going on conceptually. Now, if we want to find epsilon induced, the induced EMF around the loop, we need to use Faraday's law. But in order to use Faraday's law, we first have to determine what the magnetic flux through the loop is.
So, we know the dimensions of the loop, sort of. I mean, we know L here. The question is, what is this length here, right? And that's a little trickier because that is going to change. Now, perhaps a good name for it would be X.
After all, that denotes the position of the rod, and as the rod moves to the right, X is going to increase.
And so, if I want to find the magnetic flux, phi B, I'm going to say, and I'll do this just again for, it's a bit overkill and we won't do it every time, but just to get used to it. I will choose dA into the page in the direction of B because I can.
dA could be into the page or out of the page as long as it's perpendicular to the loop. And since B is into the page, well then,
it seems nice to put dA into the page. My flux is going to be B, the original B, times the area of the loop, cosine of 0, which is 1. And so this ends up being B L times X. That is my flux.
Now that's a little weird compared to what we just had, because before we had a function of time. And we're like, well, okay, well that's fine. I get it. Like, it's, if phi b is a function of time, then d phi b dt is the derivative. I can compute that. But here I don't really have an explicit function of time. I have an implicit function of time because x does depend on time. X increases over time.
But how do I put that into Faraday's law? Okay, well, so let's have a look. Here we're going to get Faraday's law. That's going to say epsilon induced is minus d phi b dt. Okay, well, that's minus ddt of what I just found, blx. And of course, derivatives don't care about constants, so b and l can come out. I just get dx dt. Okay, and this is on you. Nobody will tell you. dx dt, by definition, is v. So this is going to be minus blv. But that is on you. It is on you to label x as the distance. It is on you to realize that you get dx dt, and then to conclude that dx dt is equal to the constant speed v with which the rod moves to the right. In fact, it wouldn't matter if it's constant or not. Dx dt, by definition from kinematics, is the velocity in the x direction.
So yes, an old memory from mechanics, but that's how you're going to apply Faraday's law to find epsilon induced. Okay. Now, because of the induced EMF, the light bulb glows. What is the power of the light bulb? Okay, and assume that the light bulb has a resistance R. Okay, so that's the second question. Like, well, okay, fine. I found that there's epsilon induced around the loop. Epsilon induced, by the way, is what drives I induced. So epsilon induced is counterclockwise. That drives I induced counterclockwise. And the power dissipated by the light bulb is going to be R times I induced squared by definition. So I'm going to say that P is R times I induced squared. Okay. Then, okay, well, the question is, what is I induced? Okay. So to find I induced, well, I should apply Ohm's law, right? And so I'm going to maybe do it this way. Let me move this down here. Let me just put Ohm's law here. Right, and you can do it in different order, right? You can always write Ohm's law after this if you want and then find P later, but just to do things in order, let me find I induced. It's going to be the absolute value of epsilon induced divided by R, and that's going to be BLV divided by R. Okay, I'm not going to box that because that's not really what I want to find, but the power dissipated by the light bulb, which is really just a resistor that produces light, so it's R I induced squared, is going to be equal to B squared L squared V squared divided by R squared times R. That's just going to leave R in the denominator. And this is going to be the power dissipated by the light bulb. Okay. And then the last two questions are, what is the magnetic force exerted on the rod? And what is the force that must be applied to the rod to maintain its constant velocity v to the right? Which are great questions. Okay, so this is how you find epsilon induced and I induced. Fair enough. This is then what you have in terms of the rod and the current flowing through it, right? We know the direction of the current. And we have the following situation. Okay, so this is going to be my rod. Okay. And I know a few things. I know I induced flows counterclockwise, which means I induced flows up the rod. I also know that I have B into the page and B induced out of the page. And therefore, I know that I have a current, I induced, that flows through two magnetic fields, B and B induced. And I know that a current flowing through a magnetic field is going to experience a magnetic force. The question is, it is I induced, that's the only current, but which magnetic field do I choose? Do I choose B or B induced to do the right-hand rule and to compute the force? Okay. Now this is super important. I've said it many times. I will say it again. I induced creates B induced. Therefore, I induced cannot feel B induced. It can only feel the original B. This is the same thing as Q, a point charge, creates an electric field everywhere around it. It cannot then say, oh wow, an electric field. Let me experience the electric force because I'm now in an electric field. It's like, no, you created it, you can't feel it. Now you could put Q in a different electric field, you're going to get an electric force on Q, yeah. But it's the same thing here. I induced creates B induced, therefore it does not feel B induced. So I induced is going to interact with B by the right-hand rule, forefinger pointing along I induced, middle finger into the page. My thumb is going to point to the left. That is going to be the magnetic force applied on I induced. Okay, and that is going to have a magnitude, FB,
which is I induced times the length L of the rod. Right, this is L. B, sine of the angle between I induced and B, which is 90, because B goes into the page. Okay, now I induced is B, L, V over R, multiplied by L, multiplied by B. Okay, we're going to get B squared, L squared, V divided by R to the left, which in fact makes sense. Again, induction is based on a change in magnetic flux. The reason the magnetic flux increases is because the rod moves to the right. The magnetic force is trying to oppose that, right? It points to the left because it doesn't want the rod to go to the right and increase flux into the page. Now, I'm not saying that the magnetic force wins. It doesn't, yank the rod back into its original position, but it is the response. It's trying to oppose the increase in flux. It just doesn't win. And the reason it doesn't win is that, of course, it's a response, right? So if you have an effect, the response cannot be stronger than the effect. That doesn't make any sense, right? So the force, yes, FB will be to the left, but it will never be strong enough to pull the rod back, okay? Now, which, of course, brings us to question 4, which is like, well, hold on, it's FB to the left, but there's got to be some force to the right, yeah? Because, there's no way. If I only have FB to the left, the rod slows down and eventually turns around. So there has to be some applied force. And there is, and at first the applied force, will move the rod to the right, cause I induced, and then you'll get FB that's going to oppose the applied force. But eventually both will become equal to each other because, again, FB cannot overcome F applied. That wouldn't make sense. Right? It's a response. It cannot be greater than the cause. So we have F applied. Somebody's pulling this rod to the right or something. Okay. Now, if that's the case, then, well, what is F applied? Okay. And we know it's to the right, and we can figure out what its magnitude has to be because we're told that the velocity of the rod is constant. Okay. So if the rod has constant velocity, that implies that the acceleration in the x direction is 0. Let's just be clear that this is the x direction. Okay. Which means that the net force in the x direction, which is equal to max by Newton's second law, has to be 0, which means that F applied minus FB has to be 0. So in other words, F applied has to point to the right, and in magnitude has to be exactly equal to FB so that the velocity of the rod remains constant. So it's going to be B squared L squared V divided by R. Okay. So this is an extremely classic and therefore extremely important problem. These are very important questions: finding epsilon induced, finding I induced, the direction of I induced, being able to recognize that dx dt is v, being able to find the force, both applied and the magnetic force acting on the rod as it moves to the right. You will find that there are many problems that are based on the rod on rails, this is kind of the OG rod on rails, right, with the classic questions. And then there are variations that are based on this, and so if you know how to approach this problem, maybe you have to put in a little bit of thought, but you typically know how to approach the other ones, right, all the variations. And they're extremely common on exams. It's not even funny. And not just midterm 2, also, of course, the final, if you wind up having an induction problem or induction being part of the problem, then, you might find it in there too. So I would strongly encourage you to practice the rod on rails problem and the variations of it. I would also strongly encourage you to just, when you approach induction, recognize that induction is a change-based phenomenon and wonder what is causing the flux to change. Is it that B changes with time? Is it that the area changes with time?
If you want to make problems a little challenging, you could do both at the same time. It's always interesting. But you have to figure out why phi b, the magnetic flux, changes with time. Then you have to be able to write the flux, and that's almost more important than Faraday's law. I mean, obviously Faraday's law, you have to know how to apply it and how to take a derivative, which in some rare cases can get ugly, but the most important thing is to be able to write flux. And so the best way to get good at that is to see a whole bunch of different scenarios where you have to compute flux. So induction is a misleading chapter in that it is an extremely short chapter when it comes to formulas. We have Lenz's law and Faraday's law, and that's it. But it is an extremely dense chapter when it comes to conceptually understanding what's going on and then knowing how to take the very little information that you have and apply it to different scenarios where there is a changing magnetic flux. So it's definitely worth spending time on. It's a classic theme for midterm 2, of course, because it's one of the new chapters, but even for the final, if you get induction on the final, don't be surprised. Out of the 6 problems, usually 2 are from the older stuff and 4 are from the newer material. And so it's a chapter that, that with magnetism is kind of the bulk of midterm 2 and a big chunk of the class for that matter. So worth spending some time on. Again, my goal was to hopefully, I didn't want to oversimplify it, but I also didn't want to go crazy with too many details. Keep in mind that it's the changing flux that matters. Make sure that you can, first of all, recognize that flux changes and then quantitatively, write down how flux changes. Find phi b as a function of time, just like we did in these 2 problems. Hopefully that kind of helps you get started on these different scenarios that you might encounter with induction. So that was all I wanted to say today. Next week we are moving on to the joy of EM waves, which are not that bad actually. And then from there, optics. It's my understanding that optics is not on the exam, so we should be right on time in terms of covering the material, although I will live stream during the week of the exam and cover optics anyway. So with that said, best of luck. I know it's going to come up quick. A lot of you have had a lot of questions about all this stuff, and we're getting close to the second week of November. So make sure that you have enough time in front of you to go over this stuff, because there's a lot. Magnetism is a lot. Induction is a lot. And then EM waves are not that bad. You just need to practice them enough that you know how to solve these problems with finding the electric field and the magnetic field and whatever. So anyway, if you have questions, as always, feel free to reach out. Thank you for watching. And if you need help with Physics 8B, you should let me know, or you should sign up for one of our study guides if you find it helpful. It's going to have all the problems solved in each chapter and the old exams with solutions, and they're all explained in video format so that you can listen to it multiple times, rewatch it multiple times, and I always try to present how I think through a problem and what the steps are to set it up. So the goal is to kind of learn how you would approach a problem. It's kind of like what we do here, is just the problems get harder because, I throw in harder problems in the chapters, and I also, with the old exams, eventually you get to harder problems just there as well. So anyway, that is an option, but make sure you practice, and make sure you practice on problems that have solutions. So whatever problems you decide to solve and to practice on, make sure they have solutions so that you can catch your mistakes, whether they're just computational sign errors and silly stuff like that, or more, deeper, more conceptual errors that you want to clear up before heading into the midterm. Anyway, hope you have a great weekend. I will see you next week, and we'll talk about EM waves. Take care.